Welcome back to your physics notes. So what we're going to talk about real quick is Newton's law of universal gravitation. So now Isaac Newton studied lots of things over the course of his life, and one of the things that he focused on was gravity. And we call this the law of universal gravitation because he was the first one to describe the objects that are moving through the sky, like stars and planets and stuff like that, as being under the same forces as something like an apple falling towards the ground. So we call it universal because it applies to everything, and specifically applies to everything with mass. So if I had a situation involving two objects, and we said this one has a mass m, let's call that m1, this one has a mass m2, they're separated from each other, their centers are separated, oh, I kind of missed, by this distance r, I might ask, what is the force of m1 on m2? What is that equal to? Well, Newton's law of universal gravitation is what we use to find the answer to that. It describes that force as being equal to this constant g, which I'll talk about in a second, times the mass of each of the objects divided by the radius between them squared. And there's a little negative sign in front of it. So that is the force of m1 on m2. Now remember that forces are vectors, so you have to ask yourself, well, what direction is that force? And that's where that negative sign comes in right there. If you look at it the way that I've drawn it, r is also a vector. It's a position vector pointing all the way over here. What this negative sign tells you is that the direction of the force on m2 is back along that way right there. Okay. Now, if that's kind of confusing, that negative sign, just remember that forces are vectors. So anytime you have a negative sign with a vector, all it's talking about is direction. So what you need to do when you see that is just ask yourself, which direction should this be? Gravity is always an attractive force. It always causes masses to come together or be attracted to each other. So it always will point towards the other object. Now, I could ask you the exact same question, but about this guy, what is the force of m2 on m1? And you would do the exact same thing. You can answer this two ways. You could say, well, I'm just going to plug it into the formula. It's going to be the masses, m1 and m2, over the radius squared, and you can see that's exactly the same. But now it's going to be back this direction, because it's attractive. And you could have also answered that by saying, well, I know by Newton's third law, for every force, there's an equal and opposite reaction force. If this mass pulls on this mass, and it does it with a force F, I know that this mass must pull back with an equal force in the opposite direction. So that's how you apply Newton's law of universal gravitation. Now, to get an actual number, you'll need a few more details. For example, these are values you'll need to know. But I'll give these to you. So these aren't things you have to memorize. They'll always be given. G, which is that big capital G, that's called the gravitational constant. Now you'll notice this is a super, super tiny number. If I was going to write this out, it would be 10 zeros, a decimal, and then 10 zeros followed by 6.667. So it's a super, super tiny number, and that's called the gravitational constant. Now, we don't know why this is so small. It's interesting, though, when we look at forces, we have some fundamental forces that we study in physics. Gravity is one of them, and gravity is by far the weakest of the fundamental forces. And we multiplied by this number to find our values for the force. We don't really know where this comes from, why it's so weak. That's one of the things that modern physics is looking at and see if gravity is impacting the universe in some other way that we can't observe. But as we know right now, it's a very, very weak force. But when you have very, very massive objects like planets, it can add up to be significant. Other values you'll need to know in a second are we can measure the mass of the Earth. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. So just like this was a super tiny number, you can see that this is orders of magnitude bigger. This is a very large number. The Earth has a lot of mass to it. And then the radius of the Earth is 6.39 times 10 to the 6th. Also a big number. But about 6 million meters is about the radius of the Earth. So right now you're about 6 million meters from the surface of the Earth, from the center of the Earth. Now, here's some details about Newton's law of universal gravitation. Remember, forces are vectors. So think about that negative sign. All it tells you is makes you think about which direction that should point. Gravity is always attractive. We haven't yet figured out how to make anti-gravity. We don't know how to make it. If we could, it'd be nice, but we so far don't know how to do it. Okay, so now we could look at some problems, and one thing that you might be wondering to yourself already is, well, we've talked about gravity before in physics class, and so far we've talked about G. So what is G? That is the next question we'll need to answer. So if we look at a problem, so let's say we take the Earth, so here's a picture of the Earth. So that's the Earth, and let's say that this is Mr. Yale standing out in the Atlantic Ocean someplace. Okay, he's standing right on the United Kingdom. So the question that I have is, what is the weight or the force due to gravity of the Earth pulling on me? Well, I should be able to find that the force due to gravity is going to be equal to the gravitational constant times the mass of the Earth times the mass of me, so the mass of Yale, all over the distance from the center of the Earth that I am, which in this case, since I'm standing on the Earth, is going to be the radius of the Earth squared. So if I now plug in some numbers and put this in my calculator, the way I would do that is G is 6.67 times 10 to the negative 11th, and I can put my units. The mass of the Earth is 5.97 times 10 to the 24th kilograms. And the mass of Mr. Yale, so I'm about 200 pounds, which works out to about 91 kilograms. You put that all over the radius of the Earth, which is how far away I am from the center right now, and it's 6.39 times 10 to the 6th meters, and that value is squared. So now if I do that and I plug it in to my calculator, I will come out with a number of 887.4 newtons. Okay? So that is the force that gravity is pulling on my 91 kilograms of mass right now based on my position. So what we know about physics is we should be able to find that a very similar answer in a similar way. So what if I take the mass of Yale times G, which is what we've been using so far in class? Well, if we do that, you've got the mass of Yale, which is 91 kilograms, times G, which we use 10 often, but I'm going to try to make it even more precise. 9.81 meters per second squared is the average value on Earth. So if we multiply those together, we get, let's see, 892.7 newtons. So you compare these two numbers, they are pretty close. In fact, they're off by less than 1%. Okay? So what that tells you is these two things must be kind of related, and in fact they are. If you look at this equation and this equation, the only thing that is different, you have my mass right there, okay, times some value. And if you look at all of this stuff, you notice that these things aren't going to change unless I go away from the surface of the Earth. Well, those values right there are where we get G. If I take G times the mass of the Earth divided by the radius of the Earth squared, and I plug those numbers into my calculator, I get about 9.81 meters per second squared. Okay? So that is what G is. This is G. Now, the reason we do that is because if you think about it, if you're somewhere else on Earth, like let's say I go over here, and let's say this is even a different person, the only thing that changed from going over here and looking at a different person is the mass of that person. The radius from the center is going to be pretty much the same. Now you might say, well, what if you go down in a valley or To the bottom of the swimming pool or to the top of a mountain? Well, if you look at the scale of the Earth, it's going to be a pretty insignificant change. For example, we can look at a problem. So let's look at the International Space Station. Okay, so the International Space Station, or the ISS, orbits surprisingly low. You may think it's pretty high. It's at 205 miles, which works out to about 330 kilometers above us. Okay, so what would my weight be on the International Space Station? I'm weightless, right? Isn't that what they always say when you look at the videos and stuff like that? Well, let's go ahead and convert this. So 330 kilometers is going to be equal to 330,000 meters. Okay, so what would my weight be? Well, first we got to look at the radius. So the radius of the Earth is 6.39 times 10 to the 6th meters, plus you would have to add 330,000 more meters, and you get my new radius for the ISS, which is going to be equal to 6.72 times 10 to the 6th meters. Okay, so now I have a new radius. My mass didn't change. The mass of the Earth didn't change. The only thing we're changing is how far away I am from the Earth. So now you might look at it as if this is the Earth. Here's the International Space Station right here. So what is my weight on that compared to what it was when I was on the planet? Okay, well, my weight, the F of G for me, is going to be that capital G times the mass of the Earth times the mass of Yale all over this new radius, the radius where the International Space Station is squared. So if I plug all those numbers into my calculator, I get 802.4 newtons. Now remember, on Earth, I was 887 newtons. So if you compare those numbers, you notice that's not a big difference. You are definitely not weightless, even when you're in space. So the question that comes up then is, why do you feel weightless? So you've seen the videos of people on the space station. They're definitely floating around, and it looks like they don't weigh anything. So why do you feel weightless? Well, let's look at that question. Well, you feel weightless for the exact same reason that if you jump off a roof, you're going to feel pretty weightless, okay? You're going to scream on your way down. You're not going to feel anything until you hit the ground. Or in an elevator, when the cord snaps. The reason you feel weightless is because there's no normal force. So a much better term for this, weightless, what we talk about for people that are in the space shuttle or on the International Space Station, really shouldn't be weightless. It should really be normal forceless. Now, nobody calls it that. I'm going to go ahead and patent that. That's my term. When you're normal forceless, it feels like you're weightless. You're really falling towards the Earth. The problem is the floor is falling towards the Earth too, so it doesn't actually apply any upward pressure on you, so you don't feel like you weigh anything. So, why in orbit? So if you think about the International Space Station, why does it stay up there? So how does it fall towards the Earth and be weightless, but it doesn't actually ever hit the ground? Well, if you think about it, the ISS is falling, but it always misses the Earth. So the example that we often use for this is Newton came up with a mental model to describe this, and he said, so theoretically, remember we didn't have any International Space Stations back then, Newton said if you have the Earth and you have a mountain on the Earth that's really high, and you build an incredibly impractical cannon, okay? If I fire cannonballs out of this thing, and let's say I can put different amounts of gunpowder in there so they go different distances, well, if I fire one cannonball, it might go that far and hit the ground and stop. Well, if I increase the speed with which I fire the cannonballs, they will continue to go farther and farther distances before they hit the ground. Well, if I keep doing this logically, it sounds and it serves that there should be one speed that I can fire the cannonball at that it keeps going. And it keeps missing the Earth. So for every inch that the cannonball falls, well, the Earth is curving away from it, so the cannonball keeps missing the Earth. That's how objects stay in orbit. The International Space Station isn't very high up. It would look not even as high as this cannon is off the ground compared to the Earth. But it's going extremely fast laterally, sideways. It's accelerating towards the center of the Earth, but since it has so much velocity in this direction, as it moves, it keeps curving and falling, but never actually hitting the Earth. So that's how objects stay in orbit. So if you want an object to be in orbit, you have to put it up there at a right distance, give it the right velocity, so that it's moving fast enough around the planet so that it keeps falling and never actually hitting it. So that's a little bit about the force due to gravity. That was a longer video than I wanted to, but you had some extra information and some of my better artwork to date. So I hope you enjoyed it. Have a good day.